All right, so hopefully after the last video you were thinking, okay, angular velocity, that's pretty much just like regular velocity. So yeah, we got this rotational velocity omega. That's really similar to velocity. That's kind of our linear analog for rotational velocity. So we know we're dealing with something that like deals with velocity. And then the other one's a little bit of a stretch. It's a little bit harder to think about. But so we said that our rotational inertia, this I, that thing's analog, this quantity's analog is the mass. We said, hey, how hard is it to make an object accelerate? That was based on the mass. We said, how hard is it to make an object angularly accelerate? That's our rotational inertia. That's our I. So we're dealing with kind of something with mass and something with velocity. We already dealt with energy, so that's kind of off the table. So hopefully maybe this idea of momentum popped into your mind. So momentum is what we're going to be looking at, and not just linear momentum, but this new idea of angular momentum. And this angular momentum is really what allows us to figure out how the skater's working, how that sphere is working, and then eventually how come that cat could rotate the way that it did. So just kind of going through and looking at our linear analog and our angular analog like we've done, we said, okay, well, momentum is based on the mass and the velocity. And we said, okay, momentum is a conserved quantity that's related to the linear motion of an object. So the initial momentum equals the final momentum. It's conserved whenever we have a collision. And we have this idea that during a momentum occurrence or collision, if the mass is going down, if the mass decreases, our velocity has to increase in order to keep momentum conserved. And we're going to use it when we have like a collision or some sort of change in mass. And if we're looking at our new ideas, this angular momentum, we're going to use a capital L to represent it. I don't know why. Momentum seems to get the short staff here where we're saying, or short straw, I don't know what the expression is. Momentum gets P and it gets capital L for angular. So angular momentum is conserved whenever we have something related to the angular motion of an object. We're going to stick with the same idea that the initial angular momentum has to equal the final angular momentum in these cases when we're dealing with a closed system. And we're going to say, hey, our equation for this, it looks just like our equation for linear momentum, except for now it's angular. So instead of P for momentum, we have L for angular momentum. Instead of the mass, we have I for rotational inertia. And instead of velocity, we have angular velocity for angular velocity. And then just like we saw with momentum when we dealt with that before, if the moment of inertia is decreasing, that means that our angular velocity has to increase. So we have to make sure that this equation is kind of balanced. And I think I have a little thing here. So we have, if we have a big I and a low omega, a low rotational velocity, if we have some event that's going to change anything about our mass or the distribution of our mass, if we have this change, then our angular velocity has to change to account for that, to keep our quantity conserved. So when we're dealing with ice, which is like this nice frictionless surface, in this case we saw, okay, well, our rotational inertia, it went down. So that means that our angular velocity has to go up in order to conserve that angular momentum. So that's exactly like what you guys want to do when you played on that green disc, that thing where you spun on it and would bring your hands in. Same idea. You're decreasing your your rotational inertia, and then by default, because momentum's conserved, increasing that angular velocity. So that's a brief little overview of our equation. Next, we're going to get to this cat explanation. So I'm going to show you, I'm going to link a Smarter Everyday video that is cool and does a good job, but I feel like usually he does a little bit of a better job explaining it, and this one's a little bit rough. So we're going to go over, explain it together, and then I'll give you some practice problems to try out. All right, cool.